Hello friends, today we are going to learn some problem. Okay, the problems related with that is gas loss. Read this the first problem. The volume occupied by a given mass of the gas at 298 kV is 25 ml at 1 atmospheric pressure. Calculate the volume of the gas if pressure is increased to 1 atmospheric pressure. This is 1 atmospheric pressure at constant temperature. Now, what is given in this problem? Look this. The first pressure, 1 atmospheric pressure. Then, the second stage pressure is increased. Of course, is what they have given that one stage, first stage and second stage. So, P1 is equal to 1 atmosphere, P2 is equal to 1.25 and V1 in this first stage 25 ml and you have to calculate in second stage V2. So therefore, according to Boyle's law, this is V. The P1 V1 is equal to P2 V2 at constant temperature. So in this problem we have given this important term at constant temperature. That indicates this problem is based on that particular what the Boyle's law. So therefore, rearranging this equation V2 is equal to, you have to get this P1 V1 divided by P2, put down this value, you are getting that dV2 20 ml. Therefore, the volume occupied this way, V2 is equal to 25 ml. The next point is that Gay-Lussac's law. Now, this is related with the pressure-temperature relationship. Pressure-temperature of gases, how that is here related with each other. Now, what is this statement? Look this statement, at constant volume, pressure of fixed amount of gas is directly proportional to its absolute temperature. At constant volume, okay. So pressure of fixed amount of gas is directly proportional to its, that is absolute temperature. So mathematically how you write? This is where pressure is directly proportional to its that temperature, absolute temperature. Therefore P is equal to K into T. So P upon T is equal to that constant T, where K is that proportionality constant. So this is the P upon T is remain constant at constant volume and this N is the number of moles. Now if you plot this graph, okay, so P versus that is temperature, then you are getting that straight line. Okay, so at constant volume, so in graphical representation, P versus that T, you are getting that particular straight line. If that is V1, V2, V3. So such a constant volume, this is called as isochore. Okay, so this is isochore line. Now the next point is the Avogadro law. What is its statements? At constant pressure and temperature, or at the same pressure and temperature, equal volumes of all gases contain equal number of molecules. Suppose A and this is B. A and B, these are two gases and having equal volumes. Okay, both having. So that time both volumes of these gas contain equal number of molecules. How do you write mathematically? Look here this. Volume is directly proportional to the N. Okay, N is the number of moles in that particular volume. Therefore, taking V equal to proportionality constant K into N, and therefore V upon N is equal to K. That is, this term is the constant. So at constant is what? At constant pressure and at temperature. Okay. So this is. Now Avogadro given that particular term, that is molar volume. What is molar volume? Molar volume is nothing but 1 mole of any gaseous molecules. 1 mole of any gas occupies that volume is the 22.414 liter per mole at Stp condition. Okay, 1 mole of any gas molecules occupies the volume 22.414 liter per mole and STP condition. Here STP, standard temperature and pressure condition. What is standard temperature? Temperature is the 0 degree Celsius, that is the 273.15 that Kelvin, and pressure is 1 atmospheric pressure. So that is 1 atmospheric pressure is the requirement condition. Okay, so this now the next point is relation between molar mass and density of gas. Okay, look here. Now we know that number of moles of any substance or number of moles of gas is equal to what? Small m divided by what is small m? Mass of that gas, and divided by capital M is the molar mass of gas. Okay, so putting value of this n, put down this number of moles n value in equation what? This is equation V is equal to K into V. So what is this equation? You know that the Avogadro law. So from this equation you will get this V equal to K into n. Okay, so put down here n value. So this is n value putting here, and then rearranging this equation for m molar mass. So m is equal to you have to get down K into m small m upon P. But small m upon P is what? Density of gas. Okay, so density is nothing but mass divided by volume. That's why put down here value of this term, that is density, and you are getting that m is equal to K into D. Okay, or this density of gas is directly proportional to the m is a molar mass. What is conclusion? So density of gas is directly proportional to its molar mass. Okay. Now the next point is ideal gas equation and its derivation. We will see this the points. Okay. What is ideal gas equation? Those gases which obeys gas laws. Okay. Those gases which obeys the three gas laws: Boyle's law, Charles' law, and Avogadro law. Then that such gas is called as ideal gas equation. Okay. So the gases which strictly follows the gas laws, and that gas is nothing but ideal gas equation. But practically ideal gas does not exist. However, the real gases can show this behavior, shows like ideal behavior under certain specific conditions. Real gases like that, the hydrogen, oxygen, or that nitrogen. Okay. Now we will see the derivation of this ideal gas equation. How you derive this the ideal gas equation derivation? By combining three gas laws. Okay, so here these the three gas laws. First one is this: volume is inversely proportional to the pressure at constant temperature and at the number of moles. Okay, so this is Boyle's law. What is Charles' law? Volume is directly proportional to temperature at constant pressure and number of moles. Okay, what is the third Avogadro law? Volume is directly proportional to the number of moles at constant pressure and temperature. Okay. By combining all these above, you are to equating these three laws. So you are getting this proportionality constant. You are getting equating. Then that time you are getting like this. Volume is directly proportional to the n into T upon T. Okay. So therefore, by introducing that is the constant, that is gas constant. So this equation convert like this: V equal to R into n into T upon that T. Okay. So rearranging this equation, you will get this: PV is equal to nR. Pressure into volume is equal to n into R into T. Okay. So this is called as ideal gas equation. PV is equal to nR. Now ideal gas equation is also called as what? Equation of state. Why? Because this ideal gas equation describes state of an ideal gas. This equation describes the state of an ideal gas. Therefore, this is also called as equation of state. Okay. Now we are going to study here values of R in different units. Okay. R is what? Gas constant, which is called as universal gas constant. You know that the ideal gas equation PV is equal to nRT. This equation containing R is the gas constant. Okay. So for all gases, that value of R is remains same. So that's why it is called a universal gas constant. Now we'll see this first, the different values of R in one by one. R in SI unit, that is in joules. So if you fix up here, if SI unit of this pressure in Newton meter inverse to Newton per meter square or Pascal. The temperature in Kelvin and volume in meter cube. So we know that PV is equal to nRT. Rearranging this equation, you are getting this for R. R is equal to PV upon N into T. So therefore, put down value of pressure. That is the for that the pressure is the Newton meter square. So that time 10 raised to 5 Newton meter inverse cube into 22.71 liter. Now this liter is converted into you are to meter. Therefore multiply this 10 raised to minus 3. So this is the new STP condition. 1 mole of any gas occupies a volume 22.71 liter per mole. This is the new STP. New STP condition is what? New STP condition is nothing but the 1 bar is equal to pressure you are taking 1 bar is equal to 10 raised to 5 Pascal. And in old STP condition, pressure is 1 atmospheric pressure, and that value is the 1.013 bar. Okay. So here both STP conditions are generally used here. Now in both conditions, temperature is the same. Temperature is the in both conditions is the same, 273.50 Kelvin. Now therefore putting this value in like this, and you are getting R is equal to 8.314 joule per Kelvin per mole. Okay. Now this is in second. R in liter atmosphere. Second value. If pressure in atmosphere, okay, volume in decimeter cube, and temperature is that is Kelvin. Okay. Now we know that the pressure in 1 atmospheric pressure, we have to put down this value. Volume in decimeter cube. Okay, 20. This is old STP. So that time 22.414 liter, and N is the 1 mole, and this is temperature is the 273.15 Kelvin. So therefore we are getting the second R is equal to 0.082 liter atmosphere per Kelvin per mole, or 0.082 decimeter cube atmosphere per Kelvin per mole. Now the third one. This is the R in calories. We know that 1 calorie is equal to what? 4.184 joules. Therefore, we just convert this. We know that the value of that in joules is what? 8.314 joule. Okay, so just you are converting calorie. Divide this 8.314 divided by this 4.184. Getting the 1.987. This approximately taken as the 2 calorie. Okay, so that's the 2 calorie Kelvin inverse mole inverse. This is that the third value of that particular R. Now the next point is this expression for molar mass, that is M. Now by using that ideal gas equation, we know that ideal gas equation used to determine molar mass of compound. Okay. Now how is this? We will see this. We know that ideal gas equation PV is equal to nRT. Therefore rearranging the equation to get N is equal to P into V divided by R into this equation first. Okay. But number of moles, okay, number of moles is equal to what? Given mass divided by the molar mass of that substance. Okay. So therefore N is equal to small m. Small m for mass of that gas or mass of substance. This is given mass, and this is capital M molar mass of that substance. So putting value of this N here. Now you are getting small m upon capital M is equal to P into V divided by RT. Turn this equation for that molar mass of that compound. So capital M is equal to molar mass is equal to small m into R into T divided by P into V. If you know this term, okay, all this term, R is already given there, but this is knowing that remaining that order, we can easily calculate. This is molar mass. Now we will see next combined gas law. Or this is that the combined gas law or combined gas law getting. Now the ideal gas equation again is using this equation, ideal gas equation, PV is equal to nRT. On rearranging this equation, P into V upon T is equal to N into R. But N into R is a constant, and therefore How getting like this equation? P1 into V1 upon T1 is equal to P2 into V2 upon T2. Okay. Now what is this P1, V1, T1? So if the gas is present in state 1, initial state, final state, first state, second state, the way of that. So gas under two different sets of conditions. So that's why like this P1 into V1 upon T1, P2 into V2 upon that. So this is equal to like this. So this form of an ideal gas is called as combined gas law. The next point, Dalton's law of partial pressure. What is that partial pressure? You understand? Suppose the gas A and gas B. Okay. Now this gas A, this is like that molecules, and gas B, this is that molecules. This is gas 1 and this is gas 2. Now when these gas 2 mix with each other, in that time each gas is having certain its own pressure. Okay, so it can having its individual pressure, and that's individual pressure is called as a partial pressure. Okay. Now that's why statement is like this. What is statement of Dalton's law of partial pressure? The total pressure of mixture of two or more non-reactive gases. Okay. So that is the sum of the partial pressure of the individual gases in the mixture. Okay. Means it here, when two non-reactive gases mix with each other, two or more non-reactive gases mixing with each other, that time the total pressure is developed, created. So that total pressure is nothing but what? The sum of the partial pressure of the individual gases. Okay, so that's the partial pressure of individual gases. There you have to total sum. So that is the way of that, the statement of this Dalton's law. Okay, so therefore A plus B. Okay, we mix with each other these two gases. That time total pressure is developed. Okay, so the way here, and that total pressure is developed is nothing but the partial pressure of each individual gases. So therefore, how do you write mathematically here? So the way of writing mathematical explanation of this total pressure here PT is equal to, what is that? Suppose P1 P2 plus P3. This is okay. So and constant here volume and number of moles. Okay. So total pressure is equal to P1 plus P2 plus P3. So P1 plus P2 means what? The gas 1, 2, 3. It's partial pressure. So partial pressure of gas 1, partial pressure of gas 2, and partial pressure of gas 3 is the sum of this. Nothing but total pressure of that particular mixture. Now the next point is partial pressure and mole fraction of gas. What is partial pressure? Each gas is having its certain individual pressure, its own pressure. That is partial pressure. Do you know that single gas also having certain pressure, and that is individual pressure, that is partial pressure. When that suppose one gas is filled in container, in that container that single gas can also exert some pressure. So that its own individual pressure, that is nothing but partial pressure. What is mole fraction of gas? Mole fraction of gas is nothing but is the just ratio of the number of moles to divided, or the number of moles to the total number of moles. Okay. So mole fraction of gas. Now we know that pressure of pure gas is given by that in ideal gas equation. Therefore P is equal to nRT upon V at constant volume and temperature. Now look here, this at constant volume and temperature, that time what happened here? This is V is a constant, T is a constant. We know that R is also constant. So therefore just remaining term is what? N. N is the number of moles, is the amount of gas. Okay. So therefore P is directly proportional to N. N is the number of moles. N is the nothing but amount of gas. Okay. Now partial pressure of individual gases, how do you write? Just written on this board. P1, P2, P3. So P1, P2, P3 means what? Gas 1, gas 2, gas 3, like this. And you have to write using this equation. So therefore P1 is equal to N1 RT upon V, P2 is equal to N2 RT upon V, P3 is equal to N3 RT upon V. This is just consideration in the equation 1. Now come here. How do you write that total pressure? म्हणजे आपण या ठिकाणी काय केलं आहे, 3 गॅस घेतलेले आहेत. ते 3 गॅस कोणते, गॅस 1, गॅस 2, गॅस 3 आणि 3 गॅसेस असणार पार्शियल प्रेशर या पद्धतीने आपण अरेंज केलेला आहे. मग या 3 गॅसेस असणार जर पार्शियल प्रेशरची आपण जर सम केली, इफ यू डू दिस द सम ऑफ दिस 3 partial pressure, then what you have to get? Total pressure. Total pressure is nothing but the sum of these partial pressure, and just write like this: N1 RT upon V plus N2 RT upon V plus N3 RT upon V. This is goes on continuing like this. Therefore, second stage is this: take this common term RT upon V. So what is remaining? N1 plus N2 plus N3. Okay, this is continue. Now what is the next one? RT upon V is equal to this N into total. N this to the base total means N1 plus N2 plus N3 just the sum of that. So that sum you have to write like this: number of moles of that total. Now come next point: mole fraction of any individual gas. How do you write mole fraction of any individual gas in a mixture? Write the way of that. Mole fraction generally denoted by X here and X1. Suppose the mole fraction of that we suppose gas 1. How do you write? Mole fraction of this gas 1 is equal to number of moles, this is 1, N1 of that gas 1 divided by total number of moles in that mixture. Okay, so mole fraction is nothing but what? The number of moles of that component divided by total number of moles of component. Okay, the given like that particular mixture. Therefore N1 number of moles, N1 divided by total number of moles. Okay, now from equation 1, how do you write that? Number of moles for 1 N1, this is that N1 is equal to, this term just convert for N1. N1 is equal to P1 upon RT upon V. This is equation. Now N total, how do you write this again? That number of moles, that total number of moles. Here just you are written like this term, same we can write this P, this is total pressure P divided by RT upon V. This equation 3. Now by combining equation 2 and 3, we have to get the X1. Okay, so X1, how you here have to get it. Now look here, X1 is equal to what? Number of moles 1, N1, number of moles of that gas 1 divided by total number of moles. Now this equation here. Okay, so X1 is equal to N1 upon N total. Now N1 and N total is what? Just see here that value. Put down the values here and then you have to get this P1 upon RT upon V, P total upon RT upon V. So RT upon V, RT upon V get cancelled. So what is remaining? P1 upon P total. Okay. Partial pressure, this is P1 divided by total pressure, and is equal to what? This is that the X1. So X1 is equal to this term. So therefore this term you have to convert like this: P1 is equal to X1 into P total. Do you understand? X1 is equal to this. Therefore P1 is equal to what? Partial pressure is equal to this X1 into total pressure. X1 means here mole fraction. So what is here? The partial pressure of any gases is equal to the mole fraction into total pressure. Partial pressure of any gas is nothing but it is the product of total pressure and that mole fraction. Its multiplication. Partial pressure of any gas is the product of total pressure and its mole fraction. Okay, this is